In the previous video, we addressed the wave phenomenon of reflection. In this one, we're going to be dealing with something a little bit more complicated called superposition. And the thing with superposition, one of the things about superposition that's different than with reflection, is with reflection we were really only dealing with the one wave pulse. With superposition, we're going to be having multiple wave pulses involved. And it can be as few as two waves that are in play to as many as really an infinite number. And we're going to treat them all the same way. The way that it works, the general idea with superposition, is that the wave amplitudes will add. Now if an amplitude is negative, then obviously you're going to add the negative number. But there's a little bit more to it than this. The idea behind it is really the important part. So the idea is that you can look at the effect of waves on a single point by just adding up the effects of each of the waves individually. And this is a powerful idea. It basically means that each wave acts independently of the other wave. And so if you have two waves in a certain that are at least momentarily occupying the same space, then you can treat the point as responding to each one individually and then add the results of those reactions together. Now let me just give you a quick mathematical background to this. So here we have we'll look at this initial picture first, and there's two wave pulses and they're traveling towards each other. Now they're both upright, so they're both on the same side of this, and they both have an amplitude of 1. What's going to happen is that when they get to the center and they meet in this region, you're going to have nothing going on. Maybe I'll use a different color. Maybe pink will show up well. So it'll be flat here. That's actually not pink at all. And when they come together, you'll actually get an overall wave amplitude of 2. Now what's really going on is that as they come together, there's a force upwards from each of these pulling up the particles around them. And when they combine together, you get more force, and so you end up getting more displacement. What's not necessarily obvious is that those forces add together in such a way that you get the additive result of the amplitudes. And so if you have two pulses that are going towards each other and they're on the same side of the medium, they're going to get this additive result. And it's a simple result. We go from 1 amplitude each to a 2 amplitude total. If, on the other hand, we have two pulses and they're on opposite sides, this one as 1 and this one as -1, what's going to happen is that when they meet, well, nothing's going to happen. There's going to be particles from this pulse trying to pull the medium upwards, and there's going to be particles from this pulse trying to pull the medium downwards. And because they're initially given, in this case, equal positive and negative amplitudes, that means that the particles on this side are pulling as hard up as the particles on this side are pulling down. The net result is that we get nothing. Nothing happens in that brief moment when these two wave pulses overlap. So what I'm going to do is show you a couple of examples of this. So this is the website that is linked to in your PowerPoint, and here we have two wave pulses coming towards each other. And one of the things that I like about this is that it shows us the individual wave pulses, even when they're overlapping each other, and then you can see how they lead to the overall result. And this is going to be something we call constructive interference. And we'll get to that a little bit more in the next lecture. But just the idea that the wave pulses act on a point here independently of each other, and then the result is additive. Now as we go down the screen, we get this interesting simulation where they're basically keeping this one wave, kind of a continuous wave, and they're treating it as stationary for now. So we're looking at everything from this wave's frame of reference. And there's another wave that's moving at a somewhat different speed. It has the exact same frequency as this first wave, but it is moving a little bit differently. And what you can see is that when a crest and a trough line up with each other, we get a flat line down here. So it's coming up again. We get this flat line all the way across. When a crest and a crest, trough and trough line up, we get an additive effect. We get a much larger amplitude than we would have otherwise. Down here we get a very similar one, and what it's doing here is it's just showing us that this same point is actually remaining stationary the whole time, and so we get this kind of standing wave. And this is going to be something that we're going to look at a little bit more in the future, because this is a structure of motion that's actually very, very important. I wanted to just finish this one up by bringing you back to this simulation, which I think is a pretty good one. And the idea behind it is that, well, we can send a pulse, but we can also send another pulse. And so here what they're going to do is, when they're both on the same side as each other, so like right here, they're both on the same side, they both have the same amplitude, and as they come up, you can see this particle right here is being pulled upwards from both sides, which is not normally the case. Because it's being pulled upwards from both sides, it's going to have a greater acceleration, and as a result, when it gets to this point, it's not at its maximum height as it normally would have been, because even though it's no longer going to be being pulled upwards, it still has momentum. It wants to continue to go upwards until acted upon by a net external force. And it is being acted upon, it is being pulled back downwards, but since it's already moving upwards, it's going to take time to get it to stop. And once it hits this arrangement, it's finally going to stop. But this is about twice the height as the individual waves were. And then out they move again. On the other hand, on this side, we can step through, you can see that each particle is now being pulled in the opposite direction. So these particles are being pulled upward, these ones are being pulled downwards. And actually I might go through this until we get a slightly better. I missed it again. Okay. So you can see what's going on is these particles here are pulling down on those ones, these particles over here are pulling up on these ones. And as we step through, we now get to the point where, while these particles are pulling down, these particles are pulling up, and they're pulling down on each other. So these ones are pulling down on these ones, and these particles are pulling up on these ones. And the net result is not too surprising. We're going to end up getting basically a flat line. Okay, so this is superposition, where we have two wave pulses in opposite directions. So just to reiterate, superposition, fairly simple idea, I suppose. You add the amplitudes. Why do you add these amplitudes? Well, it's the result of the net forces on the particles now. If you have two wave pulses that are on the same side, they're both going to be applying forces in the same direction. You get greater acceleration, and overall an amplitude that is the sum of their individual amplitudes. And on the other hand, if they're inverted with respect to each other, you still get the sum of their amplitudes. It's just that one of them is going to be negative, and they're going to be pulling in opposition to each other. Now, one of the things here is that we saw only when wave pulses were of equal magnitude as each other. But it is entirely possible that you could have ones of unequal magnitudes, and in that case, you won't get a doubling of the amplitude, or you won't get a complete canceling out of the amplitude if they're on opposite sides. But you will get an increase in the amplitude if they're on the same side, or a decrease in the amplitude of their overlapping wave if they're on opposite sides as each other.